In this lesson, we're going to look at another chi-square test, and this one is called for homogeneity. So let's establish, when do we use this? The chi-square test of homogeneity is used when we're looking at the distribution of one variable across two or more populations. So the goodness of fit was one variable across just one population. So now we've got one variable across two or more populations. A telltale sign is that you're going to be given a two-way table, but there's another chi-square test for two-way tables. Now, your hypotheses are going to be statements again, sentences. And for your null, this is where we usually have a test of, or a claim of no difference. So we say there's no difference in the distribution of the variable across your populations. And in the alternative, there is a difference in the distribution across populations. We're going to need to find our expected counts again when we do our large counts condition. And we'll look at this and why it is more logically in a second. But what you're going to be doing is your row total times your column total divided by your table total. This test is called the chi-square test for homogeneity. Make sure you don't just call it a chi-square. You may find some older rubrics where you get away with just calling it that, but make sure you specify for homogeneity. When it comes to our conditions, test, statistic, our p-value, our conclusion, this is the same as our chi-square test for goodness of fit. Okay, so it's the same as that one, nothing new. When we go to use our calculator function, this is going to be in stat calc, arrow over to test, and it's going to be option C, and this one's labeled just as your chi-square test, which is why it's easy for kids to forget the for homogeneity when you're writing out your answer. So let's go through this with an example. The Pew Research Center conducts surveys about a variety of topics in many different countries. In one survey, it wanted to investigate how residents of different countries feel about the importance of speaking the national language. Separate random samples of residents in Australia, the United Kingdom, and the United States were asked many questions, including the following. Some people say that the following things are important for being truly, and then they inserted the survey country nationality, so like for being truly American or truly Australian. Others say they are not important. How important do you think it is to be able to speak English? The two-way table summarizes the responses to this question. So we have multiple populations here. We have 3 different countries and citizens from 3 different ones. And then we are asked their opinion about speaking English. So one variable across 3 populations. We are asked, do these data provide convincing evidence at the alpha equals 0.05 level that the distributions of opinions about speaking English differ for residents of the 3 countries? So this is definitely a chi-square for homogeneity. We're looking at the distribution of one variable across multiple populations. So we're going to go through our process here. We're going to begin by stating our null, which is a statement of no difference. So I've said there is no difference in the true distributions of opinion about speaking English for residents of Australia, the United Kingdom, and the US. So notice I've added context to my null hypothesis. For my alternative, I'm stating that there is a difference in the true distributions of opinion about speaking English for residents of Australia, the UK, and the US, and I'm going to state at my alpha level of 0.05. So just notice that we don't have to really define our parameter here because we don't have a parameter. We're not looking at mu or a proportion. So let's go on to our plan where we check our conditions. I'm going to begin by stating the name of my test. I'm going to be doing a chi-square test for homogeneity. And the first thing we're going to look at is, of course, random. We want random samples from each of our populations. So I'm saying that we have independent random samples of residents from the 3 countries were selected. You'll see some people call this a stratified random sample because first we're dividing up into our 3 different countries, and then a simple random sample from each. I'm just stating that it's a simple random sample from each country. Next would be our 10% condition, and I'm going to specify for each of the 3 different countries. So 1,000 is less than 10% of all Australian residents, 1,460 is less than 10% of the UK residents, and 1,003 is less than 10% of all US residents. And then we need to calculate our expected values for our large counts. And I'm saying that all expected counts are greater than or equal to 5, and then I've said see table. Okay, so sometimes you're gonna, if you have room up above, you can add your expected counts, but it needs to be very clearly labeled. If you're not given adequate space, don't try to squish it in. Create a brand new table right here in your conditions. So let's talk about how to get expected counts. If you're not given totals for rows and columns, always begin by filling in those sums. So let's talk this cell here. Australians who think speaking English is very important. We found 690 in our sample. So what would be our expected? Well, there was a total of 1,000 Australians out of a grand total of 3,463 people that were asked, which is approximately 28.87%, and I've done a little bit of rounding. And how many people total thought it was very important? Well, 2,569. So I would expect 28.87% of the 2,569. So I would end up multiplying that to get 741.8, and I'm rounding. All right, so I'm going to put an arrow up here saying that these are my expected values. Now, I want you to realize what is it I'm actually doing. So I ended up taking the 1,000 over this times this. So another way of saying that is I'm taking the column times the row total divided by the table total. So that's what you're essentially doing for each of your expected counts. Row times column divided by the table. So pause the video now and go through and find each of these expected values. I'll do one more with you, and then I'll speed it up. So for this one, I'm going to take 713 times 1,000 divided by 3,463 to get 205.9 as my expected count. All right, fill in the rest of your table. Hit play when you're ready to check your answers. So your expected counts are now displayed. As I stated before, if you do not have adequate space, don't try to squish it in and make it illegible. Make a whole new table. I know it's a little time consuming, but show your expected counts. So let's proceed to the rest now of our do. So my expected counts are going to be needed. I'm going to need to calculate my chi-square test statistic, which again is equal to your observed minus your expected. So my observed is 690 minus my expected of 741.8. I square that divided by my expected. And I continue this. So going across that first row would be observed minus my expected squared divided by my expected. Now I'm just going to put plus an ellipsis, and I'm going to enter this into my calculator, and that gives me 68.57. I will show you how to find your expected values on your calculator. I'm going to now get my degrees of freedom and my p-value. So first of all, my degrees of freedom is equal to your row categories minus 1 times your column categories minus 1. So we have 1, 2, 3, 4, don't count your total, 4 different categories in our variable. So that's going to be 4 minus 1 times our column, we've got 3 different populations, so it's 3 minus 1, so it ends up being 3 times 2, which is 6 degrees of freedom. I'm going to sketch my chi-square distribution. I know it's going to be quite right skewed. And I'm looking for the probability that my chi-square is 68.57 or more extreme. So that's a very large test statistic. I think we can predict that we are going to have a very small p-value here. So my p-value now is equal to, of course, the probability of getting my chi-square equal to 68.57 or more extreme. So I'm going to say that my chi-square is greater than or equal to this. And to do this on the calculator, this is chi-square CDF. Lower would be 68.57. Upper, just pick some really big value like 9999. And degrees of freedom equal to 6. So go ahead, type that in your calculator, and I get approximately 0. I get a really small value, which leads me to my conclusion. Because the p-value of approximately 0 is less than my alpha of 0.05, we reject the null. There is convincing evidence that there is a difference in the true distribution of opinions about speaking English for residents of Australia, the UK, and the US. So make sure that you put it back into